Euclid's division lemma. Lemma. A lemma is a proven statement used for proving another statement. Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r.
R is greater than 0 and less than p.
Highest common factors. The greatest common divisor or highest common factor of two positive integers a and b is the largest positive integer which divides them both.
Euclid's division algorithm. Algorithm. An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. Euclid's division algorithm. To obtain the HCF of two positive integers, say c and d, with c is greater than d, follow the steps below. Step 1. Apply Euclid's division lemma to c and d. So, we find whole numbers q and r such that c is equal to dq plus r. R is greater than or equal to 0 and less than d. Step 2. If r is equal to 0, d is the HCF of c and d. If r is not equal to 0, apply the division lemma to d and r. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF.
Finding HCF using Euclid's division algorithm. Example. Use Euclid's division algorithm to find HCF of 135 and 225. Solution. Step 1. Since 225 is greater than 135, therefore 225 is equal to 135 into 1 plus 90. Step 2. Since remainder 90 is not equal to 0, therefore we apply division lemma to 135 and 90 to get 135 is equal to 90 into 1 plus 45. Step 3. Continuing the sum process, we have 90 is equal to 45 into 2 plus 0. Now, the remainder has become 0. So, our procedure stops and divisor is equal to 45 is the HCF of 135 and 225. That is, HCF 135 225 is equal to 45. The fundamental theorem of arithmetic. Every natural number is either prime or can be uniquely factored as a product of primes in a unique way. Example, 60 is equal to 2 into 2 into 3 into 5. The fundamental theorem of arithmetic tells us that there is no way of factoring the number 60 into different primes than these. This means this factorization is unique. We can factor 60 into 2 into 30, but then 30 is not prime. And if we factor 30, we finally get same primes. Finding HCF and LCM by prime factorization method. HCF is the product of the smallest power of each common prime factor in the numbers. LCM is the product of the greatest power of each prime factor involved in the numbers. Also, for any two positive integers a and b, HCF of a and b into LCM of a and b is equal to a into b. Example: find the LCM and HCF of 6 and 20 by the prime factorization method. Solution: we have 6 is equal to 2 raised to the power 1 into 3 raised to the power 1. 20 is equal to 2 into 2 into 5 is equal to 2 raised to the power 2 into 5 raised to the power 1. Thus, HCF of 6 and 20 is equal to 2 raised to the power 1 is equal to 2. LCM of 6 and 20 is equal to 2 raised to the power 2 into 3 raised to the power 1 into 5 raised to the power 1 is equal to 60. Real numbers, rational numbers and irrational numbers taken together are known as real numbers. Rational numbers, a number of the form P upon Q, where P and Q are both integers and Q is not equal to 0, is called a rational number. Rational numbers are denoted by Q. For example, 5 upon 7, 3 upon 5. Rational number have either a terminating decimal expansion as a non-terminating decimal expansion. Terminating decimal expansion of rational numbers. Theorem: let x is equal to P upon Q be a rational number such that the prime factorization of Q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative 0, 1, 2 and so on integers. Then x has a decimal expansion which terminates. Proof: any rational number of the form a upon b, where b is a power of 10, will have a terminating decimal expansion. So, it seems to make sense to convert a rational number of the form P upon Q, where Q is of the form 2 raised to the power n, 5 raised to the power m, to an equivalent rational number of the form where b is a power of 10. Example: without actual division, find decimal expansion of 13 upon 125. Solution: 13 upon 125 is equal to 13 upon 5 into 5 into 5 is equal to 13 upon 5 cube is equal to 13 into 2 cube upon 5 cube into 2 cube is equal to 104 upon 10 cube is equal to 0.104. Non-terminating repeating decimal expansion of real numbers. Theorem: let x is equal to p upon q be a rational number such that the prime factorization of q is not of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating repeating. Proof: let p upon q is equal to 1 upon 7. Here remainders are 3, 2, 6, 4, 5, 1, 3, 2, 6, 4, 5, 1 and divisor is 7. Here 7 is clearly not of the form 2 raised to the power n, 5 raised to the power m. Therefore, 1 upon 7 will not have a terminating decimal expansion. Hence, 0 will not show up as a remainder, and the remainders will start repeating after a certain stage. So, we will have a block of digits, namely
1,42,857,
repeating in the quotient of 1 upon 7. Example: without actual division, state nature of decimal expansion of 64 upon 455. Solution: let p upon q is equal to 64 upon 455. Here q is equal to 455 is equal to 5 into 7 into 13. Since denominator 455 is not of the form 2 raised to the power n, 5 raised to the power m, therefore 64 upon 455 has non-terminating repeating decimal expansion. Theorem: let p be a prime number if p divides a square, then p divides a, where a is a positive integer. Proof: let the prime factorization of a be as follows: a is equal to p1, p2 up to pn, where p1, p2 up to pn are primes, not necessarily distinct. Therefore, a square is equal to p1, p2 till pn, p1, p2 till pn is equal to p1 square, p2 square till pn square. Now, we are given that p divides a square. Therefore, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of a square are p1, p2 till pn. So, p is one of p1, p2 till pn. Now, since a is equal to p1, p2 up to pn, p divides a. Example, under root 2 is irrational. Solution, let us assume that under root 2 is rational. So, we can find integers r and s is not equal to 0, such that under root 2 is equal to r upon s. Suppose r and s have a common factor than 1, then we divided by the common factors to get under root 2 is equal to a upon b, where a and b are co-prime. So, b under root 2 is equal to a. Squaring on both sides, we get 2b square is equal to a square. Equation 1. Therefore, 2 divides a square implies 2 divides a implies a is equal to 2c for some integer c. Putting value of a in equation 1, 2b square is equal to 4c square implies b square is equal to 2c square. 2 divides b square implies 2 divides b. Therefore, a and b have at least 2 as a common factor. But this contradicts the fact that a and b have no common factors other than 1, implies our assumption is wrong. Therefore, under root 2 is irrational.